Hello, welcome. I hope you can hear me. I'll try to talk very loudly to get my voice across, but I think it should be fine. So let's get started. We were talking in class about the vector space L2, which is defined as well, the vector space consisting of all square sum both sequences. So what that means, we can write it down, is L2 is just a set of sequences x of I. This just means the sequence, such that if we sum from I through 1 all the way to infinity, every term of xi squared, this whole sum converges, meaning less than infinity, where each term in the sequence or the series is a real number. So that is our vector space that we're talking about. And the way we will treat this is as an inner product space, meaning we need to define an inner product, and we define it as follows. So if we have some vector xi and yi in L2, then the inner product is just defined as the sum xi, yi. Again, from I ranging from 1 all the way to infinity. So kind of what you would expect, given that we have this up here. So you can already think about what does like the norm of a vector mean. But we'll not exactly talk about that. We'll just go over some other features of this vector space. So the first thing we need to check is that this thing, the inner product, actually converges. So we know that every vector itself, when you square every term and add it, the stat sum always converges. But we also need to check that the vector space is, or that the inner product is indeed in our field, in this case, the real numbers, meaning that it always converges for every xi and yi in L2. So let's go ahead and check that. Delete this. And so the way we'll do this is as follows. We'll let two arbitrary vectors x of I and y of I in L2. And then we'll do some algebra and show that the expression we get, that the definition of the inner product actually converges into a real number. So let's write that down. So we'll say let x of I and y of I be in L2. And again, we want to show that x of I, y of I, which is equal to the sum from ranging from 1 to infinity, x of I, y of I, actually converges. So that's just what I want to show. We have that highlighted here. Let's go ahead and do that. So this is the proof strategy of what I'm going to do. Basically, we'll say, well, we know that x of I plus y of I is in L2, right? Because L2 is a vector space, so vector addition is still, I mean, it's closed under vector addition. Oh, I can probably tilt this up, get a little better. There we go. So we know that vector addition is that the vector space is closed under vector addition, and so we can use this fact with the definition of L2 to get to our desired result. So how we do this is as follows. So if xi and yi are in L2, if we record the definition of L2, what does it mean? It means that it's the set of all square summable sequences, which means that if we take the sum from 1 all the way to infinity of x of I plus y of I squared, this whole thing converges. And I'll just bring this all the way over here. Let me see how far can I go. Maybe around here. I should say, yeah. So this whole thing converges. And we can expand this out and start shuffling with this expression a bit. So if we just expand out the brackets, we get x of I squared plus 2 x of I y of I plus y of I squared from 1 to infinity. And we can now split this sum into 3 different sums. So this will be, let me just pull this slightly more to the side. Again, just standard procedure here, x of I squared, plus we can put the 2 out. This will be x of I, y of I, again, from 1 to infinity. And then finally, we also just this here, the last term, from 1 to infinity of the y sub I squared. This whole thing has to converge. Now here's the key takeaway here is that by the definition of L2 and the fact that we know that xi and yi are both in L2, we know that this converges and this converges. So if the whole sum converges, it has to mean that this converges. So let's just rewrite that. So that implies that 2 times the sum of x sub I, y sub I, from I is equal to 1 to infinity, this needs to converge. And we can just take the 2 out at this point. When there's multiplying by 2, if we know that that whole thing is a real number, if that whole thing converges, then of course the sum has to converge. As you know, this is just a real number. So this means that the sum from I is equal to 1 to infinity of x sub I, y sub I has to converge. Oh, again, what is this? This is just our definition here of the inner product. And then with this, we get that x sub I, y sub I converges, which is exactly what we want to show. And as we know, x sub I and y sub I here are just arbitrary vectors in L2. So really, like this is saying that for all x sub I and y sub I, we could make them more explicit. We can just write this like to have a kind of in picture form instead of just verbally. We would say then for all x sub I, y sub I in L2. And now we have the same exact logic. So that's how we show it converges. Now there's some other stuff we need to talk about. Mainly the big gap between infinite dimensions and finite dimensions in vector space and inner product spaces. There's a lot of things that hold in one and don't hold in the other, and a lot of nice properties that break, some that stay in place. But there's a lot of different intricacies that we need to consider. One of them, for example, is when talking about isometries. So we know that isometries are always 1-to-1. We prove that in homework, and it's just a very nice property we can use about them. And so if a linear transformation is 1-to-1 in finite dimensions, that has to mean that it's also onto. But as we'll show here, it's not the case in infinite dimensions, as is the case with L2, an infinite dimensional vector space. So let's just give an example then of an isometry that is not onto, and to convince yourselves that it's not in fact the case that this will always work. So let's just clear this up. Okay, so just let's recall what we want to show. Want to show that in infinite dimensions, isometries does not imply onto. So what is our strategy? Of course, just to find a counterexample. So our goal / our strategy, find an isometry, I'll call it T, from let's say L2 to L2, isometry. Okay. Such that, let me see how much space I have left here. Okay, I have a little bit of space. Such that T is not onto. In other words, we want to show well, I want to show that T is not onto. That just means that the image of T is not all of O2. Okay, so of course the first thing we need to do is find an actual isometry, or before that, find a linear transformation, prove that it is an isometry, and then show that it isn't onto. So let's do that. So consider then this linear transformation T from L2 to L2 defined as follows. So defined as, we take a sequence starting at x1, x2, x3, and so on. And we shift everything to the right by 1, and that is 0 inferred. So exactly like the right shift operation we know from many programming languages, that's exactly what it's going to be. So this becomes 0, x1, x2, x3, and so on. So we just shift everything to the right by 1. So our first step now is to show that T is actually an isometry. So what we want to show now is that T is an isometry. And if we just recall the definition, what this means is that for any, I'll call this like psi and yi in L2, if we take their inner product, we'll get the same thing as taking the inner product of t of xi and t of yi. T of xi and t of yi. Okay, so let's go ahead and do this. Do I have enough space to do it just in the bottom? I think so. I think it should be okay. Yeah. So let's actually let's be more clear and put everything on top. So I'll give you a second if you want to like screenshot or write something down, and then I'll get everything off. Okay. So let's just once again restate what we want to show here. And that is that again, let's just rewrite t so we have everything on the board. And t, I'll write it in different just in a different way, just to save space here to put it into one line, but it's the exact same thing. So t of some x1, x2, x3, and so on is just shifting everything to the right and adding a 0 in the first term. So that's 0, x1, x2, x3, and so on. And what we want to show that t is an isometry. Just repeating, just writing things down again. So that t of some xi, t of some yi is equal to xi, yi. I apologize for the slightly confusing notation here with using just one pair of brackets for t. I'm going to avoid putting two. We could write these as something like this, as like the brackets around t is what it's taking as input. But just for conciseness and cleanliness, I'll not do that. But just be aware of that little fact there. So again, that's what we want to show, and let's actually go ahead and show it. So let some arbitrary generic xi and yi be some x1, x2, x3, and so on, and yi be the exact same thing but with y's. So yi, y1, y2, so on and so forth. Both these vectors in L2. And that means that then if we take t of xi, we get 0, x1, x2, so on, and t of yi, exact same thing here, 0, y1, y2, so on and so forth. Now, what that means is that when we take t of xi and we take the inner product with t of yi, that'll be the sum of t of xi sub I times t of yi sub I from y is equal to 1 to infinity, just by that definition of the dot product. We can just actually start writing the terms out. First one will be 0 times 0 plus, then we have x1, y1 plus x2, y2, and so on. And so we find that this 0, of course, 0 times 0 is just 0. We can just take the rest of the sum and rewrite it as the sum from I is equal to 1 to infinity again of xi, yi, as we start summing from 1 and then x2, y2, x3, y3, x4, y4, so on and so forth, away to infinity. But then this is just exactly the definition of the inner product of xi and yi. And so we found that if we take the inner product of t of xi and t of yi, we get the inner product of xi and yi, showing that t is indeed an isometry. So take a moment to just look at it. If you're not sure, just convince yourself that it is true. There's no magic here. All we're doing in t is shifting everything to the right. We know that we're allowed to do that. And then when we take the dot product, the inner product of two vectors transformed by t, we're essentially just taking their inner product and adding a 0. So we're not doing anything to it. It's the exact same thing. This is an isometry that is that is crafted like that just by design, by construction. So it's really easy to see that it is an isometry. And now what we wanted to show to begin with was that we know that isometries are 1-to-1, but does that mean that they're onto? And we want to show that in the case of infinite dimensional vector spaces, that is not the case. So let's go ahead and show that T is not onto. So let's keep the first line here just with the definitions of everything. And what we now want to show is that T is not onto. So T is not onto. I.e., image of T is not equal to L2. And now we only again need to find one counterexample of something that lives in L2 and does not live in the image of T, because we know that the image of T is a subset of the vector of the whole vector space. And so all we need to find is an element that lives in L2 but does not live in the image. And just consider the following vector. The sequence that starts at 1 and then is followed by infinitely many zeros. We can just do a very quick sanity check that this sequence, let's call it alpha. Let me shift everything over. Alpha I is equal to 1, 0, and zeros all the way through infinity. And now just a quick sanity check as a side here. I'll just wipe this right after. Let's just check that. I'm sorry, that alpha sub I is actually in L2. And so we need to show that it's that the sum of its component squared actually converges. Obviously it does. We just get, if we actually do it out of alpha I squared, this would be 1 squared plus 0 squared plus 0 squared. And we'll just add more zeros all the way to infinity. It's just 1. It converges. Yeah. That means that alpha is indeed in L2. So let's just write that. We know alpha is in L2. But then clearly, just by design of T, it's not in the image of T. Because every single vector in the image of T starts with a 0, and alpha starts with a 1. So obviously it's not in the image, which means T is not onto. So let's just write that down really quickly. We can just say clearly, alpha sub I is not in the image of T. As there's no vector, we can shift by 1 to the right and at a 0 in the first spot to get alpha. It's just impossible by construction of T. As there does not exist any xi in L2 such that T of xi is equal to alpha I by construction of T. So this starts to raise more questions then on the limitations of some theorems we use for finite dimensional vector spaces that we can't use in infinite dimensions and differences between them. And we can discuss that in even more detail. So in class, we talked about the subspace of L2 consisting of the sequences with finitely many non-zero entries. And we can explore the topic a bit more to find some more pitfalls and limitations of some of the theorems we learned in infinite dimensional vector spaces. So let's put that on the board again. I just need a second to clear everything out and write it all down again. Okay, so let's read through it again just to refresh your minds. We'll call it the subspace U. So U is a subspace of L2. U, let me just check, yeah, it's in place. We define U as the set of all sequences in L2 with finitely many non-zero terms. Still fits, yeah, non-zero terms. So that's how we define U. Now we need to talk about U perp, or the orthogonal complement of U. And just start to think about some of the things we learned that we can do with U and U perp, or U and its orthogonal complement, some theorems we have here and there. So just let that linger in your mind while we go over finding the orthogonal complement of U. So what I want to do, want to show or slash want to do is find U. Let's just write go here, right? That's our goal. That's what I want to do. So go find U. We can just go straight from definitions here. We know that the orthogonal complement of U is the set of all vectors in L2 that are orthogonal to every single vector in U. So let's write that in more mathematical, more formal notation. So it's just a sequence of xi such that xi and yi take their inner product is equal to 0, just means it's orthogonal for all yi in U. So it could be a little confusing with all this math in place. But what we mean is that if U is just a set of all sequences of finitely many non-zeros, what are the vectors that if we take their inner product, we'll always get 0 for every single vector in U. And just to make things a little more clear, we can just write this as xi such that the sum from I is equal to 1 to infinity. This is just translating what the inner product is by definition of xi yi is equal to 0 for all yi in U. And here's my claim. The orthogonal complement of U is actually just the 0 sequence. And so it's the set containing the sequence that is 0, 0, 0, all the way up to the end. It kind of makes sense if you just think about it on a quick look, as if U always has a non-zero or has finitely many non-zero elements, and we need to find a vector that will like always cancel out everything for every single combination. It needs to be something very generic because L2 is infinite dimensional. So what that means is that U is also U is an infinite set, of course, and the non-zero entries can be in any single entry. Like there's infinitely many choices of where to put them, as long as we're putting finitely many of them. So we have infinitely many choices there. We need something that cancels everything out. It's obvious that if something in some other subspace that is not the orthogonal complement has a non-zero term, we can always find something in U that when we take its product, it'll not in fact be 0. That might have sounded a little confusing, but hopefully if it made sense, I'm just trying to show that a good strategy to show that the orthogonal complement is indeed just a 0 vector is to go by contradiction. So we'll prove this by contradiction. So we assume for the sake of contradiction. And now what do we want to assume for the sake of a contradiction? That there exists some other vector, some other sequences, let's call it a sub I, that is not the 0 vector in U complement, with the orthogonal complement of U. And what does that mean? That means that for all xi in U, that when we take the sum of x sub I, a sub I, has to be 0 from I ranging from 1 to infinity. So every single term, when we do that, we have to be 0. Now, a sub I is not the 0 vector, which means that in at least one index of A or one term in the sequence, it'll not be 0. That's how we define it, right? That's our contradiction. So let's write that down. So we know that there exists some index, let's call it K, right? Just in the naturals, where A sub K is not equal to 0. So that's the most general term. And so now consider the following vector in U. So consider, let's call it, what should we call it? We already used alpha before. We're talking about something named A here that we want to cancel out. I don't know. I'm very uncreative. Let's just call it beta. So consider some beta I in U, where beta I is equal to the following sequence. So we have zeros everywhere. And then at the kth index, we have a 1. And again, zeros everywhere else. This is the k index. Is it catching on screen? Just barely. Okay, so I'll move it up really soon. Actually, I think I probably won't even need to, because it should be very clear where the contradiction lies here. Well, if we just look at it, let's just convince ourselves that bi is in, or that beta I is in L2. Of course, it's the same example as we used in the isometry exercise. We only have the 1, it gets squared, it becomes 1, everything else just becomes 0, 0 squared is 0. So it's of course an L2, and it's obviously also in U, since there's a finite number of non-zero ranges, in fact just 1, that's exact 1 at the kth index. Everything else is 0, so it is indeed in 1. But then, the big but here is that the sum of a sub I, beta sub I, ranging from 1 to infinity, in other words, the inner product, is equal to, well, whatever we'd have at a sub k, which by definition cannot be 0. And so this is our contradiction here. Because we assume that a sub k or a sub I is a U perp, meaning that it's orthogonal to everything in U, and then we just found a vector in U that's not orthogonal to it. So that's our contradiction, and therefore there's no non-zero vectors in U perp. The only one we have is indeed the 0 vector. So that's how we conclude our proof. And then just as a finishing remarks, we can think about some of the things that work in finite dimensional vector spaces and break in infinite dimensional vector spaces. Now here's an interesting one. The two main ones, in fact. Let's just clear everything before we start talking about it. So pardon me, I don't remember the number of the theorems off the top of my head. So I'll just reference them by name, by their statement, by what they actually mean. But I don't have the exact number. Somewhere in chapter 6, 6C. But here they are. Well, the first one, in my opinion, or at least what I feel is the biggest one, is that I'll call it theorem 1. It's the theorem that states that if B, an inner product space, is finite dimensional, and U is a subspace of V. Just keep in mind I said subspace, so I'll just write this down. Then V is just U direct sum with its orthogonal complement. So this is obviously extremely useful. We can break down pretty much every finite dimensional vector space into a sum of a subspace and its orthogonal complement. Obviously, applications here are like as many as you'd want. It's super nice. Everything works nicely. We can talk about dimensions and everything, and things just work. And it's very nice and tidy and neat. But obviously, since we're talking about it, it means that it's not the case in infinite dimensional. In fact, we can talk about the exact same subspace, the sequences with finitely many non-zero terms. And it obviously becomes clear that if we take the sequence consisting of, I should say the subspace of sequences with finitely many non-zero terms and its orthogonal complement, which we just proved that it's just a 0 vector and nothing else, there's no way we can get all of these. So let's just write it down again. So in infinite dimensional vector spaces, or let's say, we're really talking about inner product spaces here. Inner product spaces. This theorem 1 is not true. And our example slash, which really is just a counterexample, is the exact same we used last time. So V, we picked V to be L2. Again, same inner product definition we'll be using all of today. And we say U is the set of sequences with finitely many non-zero terms. A bit, yeah, just barely. Then we just showed that that means that the orthogonal complement is the zero sequence. And now all we need to show is that, so what we want to show is that B is not in fact just U direct part with U complement. Obviously it's not, because what this, like if we take the U when U, sorry, let me just rephrase. I was being a little confusing there. So we want to show that V, let's make this more clearly, a V is not equal to the direct sum of U and U perp. Obviously not, right? Because what do we have in U perp? Just a zero vector. So in the actual sum of something in U and something in U perp, we'll just add zero to it. So it'll be exactly just U. That'll be the underlying set. And we also have that the intersection is just a zero vector, as the zero vector is in both of them because it has finitely many non-zeros. So it's also in U, and that's the intersection of U and U perp. So then we know that this is not completely true. So yeah, we can consider sequences that converge when we square all the terms that have infinitely many non-zero or infinitely many non-zero terms, right? You obviously can craft that out of a sequences with finitely many non-zero terms. So this is one theorem that breaks. Another one is theorem 2. The statement here is exactly the same, so I just keep that the same. And if we have a subspace U of V, or just a subset, then U perp is equal to U. This doesn't hold in infinite dimensions, as we'll now show, and we'll use the exact same how should I say, the exact same vector space and subspace that we have there. So if we use the exact same U, we have that U perp is equal to just 0. But if we take the orthogonal complement of 0, what do we get? Well, clearly we get all of L2 back as everything that is orthogonal to everything in U perp. So in other words, everything that is orthogonal to 0 is in U perp for UT, like the orthogonal complement of the orthogonal complement. But then everything is like by definition, if we just take the inner product with the 0 vector, we'll always get 0. All terms get sent to 0. That means that every single vector in L2 is orthogonal to 0. So the orthogonal complement of the set containing just a 0 vector is everything. So it is L2. And obviously L2 is not equal to U. So therefore, what we've shown is that U perp is not equal to U. Another theorem that doesn't hold. So yeah, that pretty much sums it up for our work we're going to cover today. As a quick exercise, or if you just want to convince yourself, try to find a sequence in L2 that belongs in L2, meaning that its square sum converges, but that it doesn't have finitely many non-zero terms. We know that they're out there. And so that means that we can reach these conclusions. So just 2 quick counterexamples using what we've shown before. And in a way, it's a bit disappointing because it's some really nice properties we could really hope to have in infinite dimensional vector spaces. But such is life when we have infinities, this kind of unexplainable thing that trips everyone up. And so these are just 2 of many different oddities that we get when talking about infinite dimensions and finite dimensions in the basis of our vector spaces and inner product spaces. And yeah, I'll stop recording now. I don't know how much time it was supposed to take. I don't know how much time I did take, but that's about it. I naturally tend to follow more of like a lesson type of thing instead of just explaining my solutions. So I hope that was okay. And yeah, hope you have a super nice break, and I'll see you back on Monday. Bye bye.